Okay, we have a 555 that we can look inside of. So this is the circuitry, and we can go probe inside and look at things, okay? So the first thing we need to think about is the block diagram of the actual device. Now, the evil scientist here, let me turn down that. The evil scientist here has this great paper called the 555 Timer Principles of Operation. It's a really, really good paper. It's free to download, go to his site, and it tells you all about the internals of a 555 and how each section works. It's probably better than this video is going to be, so go read the video, the example here. But I think I explained some things a little bit better than he explains in here. But yeah, we'll get to that. So this is how it works inside. But we need to figure out what does the block diagram look like of a 555. Okay, that's the most important thing to have in your head. And I think one of the greatest travesties over the last 50 years was nobody had a good block diagram of a 555. Yes, I'm going to say that. But he finally put together the perfect block diagram of a 555. So let's see, let's go over here, get it straightened out. This is the perfect block diagram. It's completely understandable. Most of the block diagrams are just kind of drawn to squeeze into a little square. But yeah, this is the way a 555 timer works. First of all, there's a voltage resistor string here. And it's actually 5K, 5K, 5K. Was the 555 named because there's 5K, 5K, 5K? I don't know if anybody will ever know that question, but anyway, it's claimed to not be, but I think it's too coincidental. And I think the guy who ran the group probably knew that information. He snuck it in to be a 555. Anyway. So what does the string do? Well, it creates a 2/3 voltage and a 1/3 voltage. So whatever you have on the input, you get 2/3 of it here and 1/3 of it here. And then you've got two comparators. One comparator, its job is to say, are you bigger than 2 2/3? And this one says, are you smaller than 1/3? So if you're bigger than 2/3, this one fires. If you're less than 1/3, this one fires. And what do you do with it? You put it into a flip-flop and remember it. So if it got bigger than 2/3, you do a reset. And if you do less than 1/3, you do a set. So it's just a set reset. And with any op-amp set reset, you can usually reach in and force them into a state. So there's a reset pin where you can forcibly reset the flip-flop. And then there's an output section. There's a push-pull output and an open collector output. Most people think this thing is a little bit special, but no, it's just an open collector output. It can be used for special things, but it's just an open collector version of the output, okay? And we can use it to discharge capacitors and stuff. But yeah, this is a great block diagram. I wish this had been on day one. Okay, so we're going to look inside of the part, all right? And here is the schematic of the board that we have. And in dotted lines, it shows the different parts. Here's one comparator. Here's the other comparator. Here's the 5K, 5K, 5K. Here's the flip-flop, here's the push-pull output, and here is the open collector output and the reset. So anyway, this video is going to be all about comparators. So there's one comparator, two comparators. And strangely enough, they're wired differently. And we'll talk about why that's true and take a look at the two, all right? So we need to talk about comparators, but we need to back up even a step further, okay? We need to get some fundamentals out of the way first, okay? All right. Okay, so the first thing you need to know is this is a differential amplifier, okay? And you can imagine that there's a voltage at the top, ground, and so there's some currents set up. You have currents through these two. And if these two are the same, then you have equal currents flowing in these two paths, okay? If one side is higher than the other, you'll have different currents flowing through here. And at these collectors, you'll have different voltages. And I always think of this thing as a teeter-totter, okay? It can go to one side or it can go to the other side, okay? It teeter-totters. And if this voltage is high, then this voltage goes low. If this one is high, then this voltage goes low. So when this one is high and this one is low, this one is low and this one is high. So it's an inverting teeter-totter, right? You teeter-totter here, but inside it's teeter-tottering the other way, okay? And so again, if this is high, this is low, this is high. If this is high, this is low, this is high, okay? So it's the opposite, but it's a differential. So you usually bring the signal off of one or both of these collectors, okay? If you just need one signal, just bring one. If you want the whole diff voltage, you can bring both, right? So that's a differential amplifier. Now, can we use this as a comparator? Well, yes, but what we really want is when one side is a little bit higher than the other side, we want that teeter-totter to go all the way, okay? So instead of this being a little bit and this being a little bit and these two being a little bit, we want these two a little bit, but these guys a lot, which means we need gain. We need lots and lots of gain, okay? So one way to get gain is to put in Darlington transistors. So we have a Darlington here, a Darlington here. So if each transistor has a beta of 100, a gain of 100, then you have 100 times 100. So you have lots and lots of gain in this situation. So the configuration we have here is exactly that. We have a Darlington pair on this side, and we have a Darlington pair on this side. So exactly the same as this, okay? All right, so there's an additional trick that the comparator uses, and we need to understand another circuit before we can go to that. So the other circuit is this one. Okay, this is called a current mirror, okay? And so we have a current I1 and a current I2 in these two legs here. And this transistor is wired to be on all the time. The collector is tied to the base. So any current going this direction can go around and go into the base and then get amplified and come out the bottom. But because we are starting with a known current, the transistor will just have to do whatever it needs to do to maintain that one current. So it will set up a base voltage that will create an emitter current to be equal to this I1 that we need. So the transistor will set itself up to accommodate this I1. And because the voltage conditions on this transistor are set up for this I1, this voltage is also used in the base of this transistor, and so over here you will set up a condition where I2 is exactly the same thing as I1. You've already set it up here, and then you copy it over here, or you mirror it over here, and you will get I1 equal to the I2, okay? I1 equal I2. So you have a current mirror, okay? So you can build it with NPN transistors, or you can build it with PNP transistors. It doesn't matter. As long as you connect the current collector to the base, this will do the same thing. I1 equals I2, okay? So you can do it either way. Okay, that's a current mirror. All right. So in our device, we're going to use a current mirror in a strange way. Okay, I found this circuit in Horowitz and Hill. And Horowitz and Hill was talking about comparators, and here's one used in a voltage a temperature regulator. Here's a thermistor, and then here's a heating element, and then it compares the thermistor with a set voltage here, and it does the teeter-totter between the thermistor and the potentiometer, and if it gets too cold, it turns the heater on. If it gets too hot, it turns the heater off, okay? So it's used as a comparator. It's using a current mirror down here. That should look familiar. We have 15 volts and 15K, so that sets up 1 milliamp. And that 1 milliamp is in the Q7. So if we have 1 milliamp here, we mirror it over here, and we have 1 milliamp over here. So 1 milliamp here, 1 milliamp here. In our circuit, we're going to be using a resistor here, but it's better if you use a current source, as they do here. But here we have the two Darlington pairs, but look at, instead of resistors at the top, we're using a current mirror on the top, okay? That seems really, really odd. If we wanted to go teeter-tottering, why do we have something that mirrors it? If this is one current and you have the exact same current over here, the thing will never teeter-totter, right? It just won't work. And that's the way, when I first saw that circuit, I went, well, that doesn't work. And it's very, very clever. It's very, very clever. I don't think anybody explains it really simplistically, and I'm going to today. All right, so by using, this is called an active load, okay? An active current load. It's a funny term, and I think that gets some people confused, but it is a current mirror, okay? So how does this thing work? All right, so it's gonna work two different ways. I'll explain the current thing first, okay? So the current thing is, if we have this side high and we start pulling down, this transistor turns on, we start pulling down, we'll have lots of current in this, transistor. And it'll get mirrored, we'll have lots of current over there, okay? But that's exactly what we want. Remember, when this side goes down, this side goes up, right? And remember, I said, what if you had a resistor here and a resistor here? Then this side can pull down quickly, but to pull up quickly, it has to use that resistor. Whatever resistor you have here, it's going to be pulled up with that resistor. But here, it's being pulled up with a current source. And it's pulled up with a really hard current source because this one's being pulled down really hard and fast. It's going to turn this guy on really hard and fast, and this will go up hard and fast. So it's very, very clever in that you think it would fight each other, but it's actually complementing each other. So that's very, very clever. So the other thing this does is a very clever additional gain. It adds more gain to the circuit. And you would say, how could it possibly add more gain to the circuit? It just mirrors current, okay? Well, we need to think of a simple amplifier, okay? And we have R1 and we have R2. And simplistically, the gain is R1 divided by R2, okay? So if you want more gain, you either make this one smaller or you make this one bigger. So in our case, can we make the resistor big, okay? Because we want lots of gain. Remember I told you we wanted lots and lots of gain. And we're using a Darlington, so that's lots and lots of gain, but we want even more gain. So we want a really, really big resistor here. So let's say we put in a 1 meg resistor and a 1 meg resistor. Then we'd have lots of gain here, but again, the pull-up would only be a 1 meg pull-up, so it would be very, very slow. So this solves the problem of the pull-up problem. What about, why does this act like a really high resistive device? Why does it look like a really big resistor? Well, if we look at a regular transistor and we look at the resistance of a NPN in this direction and in this direction and in this direction into a collector of a transistor, it's very, very high resistance. It can be as high as 5 megohms. Okay, so very, very high impedance going into the collector of a transistor. And what is it that we're going into over here? We're going into the collector of the of these two transistors. So they look like megohm resistors, but they don't act like megohm resistors. When you want them to be high resistive, they are. When you want them to be really, really low resistive, they are. It's a very, very clever way of doing this. So we've accomplished two things. We've made the gain super high, and we've made this pull-up very, very quick. So this thing is going to teeter-totter super, super quick, okay? So that is what we got in our circuit with one little extra change. And that is that we actually have a couple little current mirrors at the top too, all right? So those, you already have one current mirror here, and it'll go teeter-totter. It just buffers it. It's like a buffer. These guys are still going to be teeter-tottering, and you're just mirroring it. So whatever this one's doing, this one's going to do the same thing. And so it's just a way of buffering the signal so you don't corrupt these guys. It's just adding more distance between the output and the device itself. So one side gets to pull down to ground, and the other side gets to pull where? Well, it pulls whatever you're doing. So again, remember, on one side we wanted to go quickly to ground, the other side we wanted to go quickly to VCC, and that's what these guys do just as well as a single one over here. We have a double. Okay, so that's a little bit fancy. Okay, let's take a look at the second comparator. Well, what is the second comparator? Again, it's a Darlington, and it's a differential pair. But look, it's very, very different. It's PNPs this time. Okay, so we used NPNs over here, but we're going to use PNPs over here. All right, and this is not being used as much in a hard comparator situation here. This is more like a differential voltage thing with high gain. I don't know exactly why they didn't put in the extra active loads on this side. They could have, but they didn't. But what they did want to do on this side is to make it operate very, very low in voltage. Now remember, we have a 2/3 voltage, 1/3 voltage. So this side we're operating at high voltages, but this side we're operating at low voltages. So if we're operating at high voltages, then we can go on the high side on an NPN. So we're pulling it up over here. Over here, we're down in the 1/3 voltage, so we're going to use PNPs because we're going to be pulling down on it. So here our teeter-totter we're pulling down on. Here our teeter-totter we're kind of pulling up on, okay? So that's why they've done this one over here. All right, so we have a, looks like a current source set up over here. So we have a current going into the top. All right, I've redrawn the other comparator, one using the PNPs. And you can see this one's quite simple. It has a current source and then on the top, and then it has the input. I don't know why they labeled it trigger, but anyway, the input's on pin 2. The other input, the other one's on pin 6. This one is using the 1/3 voltage. The one that we looked at before used the 2/3 voltage. This uses the 1/3 voltage, so it's on this side. So when this side is lower, then the current will go this way. When this guy's lower, the current will go this way. And these guys just go to ground, and these guys go to ground, and the output comes from here. Now this one doesn't have that really cool current mirror where it would pull down really hard as it teeter-totters. This one has a 100K resistor, so it actually gets pulled up quickly, but pulled down it's quite slow. It's a 100K resistor to ground, so that was done intentionally. And so on one side it pops quick, on this side it goes slow. So don't know why that was in there. I'm sure he had a reason for it, but anyway, that's the way this comparator works. Okay, we're going to be inputting this signal into the comparator. Okay, so we will compare this against what? Against the 2/3 voltage, right? So this one goes from 0 volts to 10 volts. The ground is here, and it's 2, 4, 6, 8, 10. Okay, let's turn on the trace. Let's turn on this one here. There we go. That is the 2/3 voltage, okay? So that's one side of the comparator, and this is the other side of the comparator, all right? And then let's look at the output of the comparator, all right? And there's the output of the comparator. So when we're above the threshold, bam, the comparator fires, and then there we go. So that's how the comparator works, as we just saw. Now, if you remember, now we're looking at this comparator here, right? It's the 2/3 voltage, and then we input a triangle wave, and we're looking at the output right here. And so we've just looked at that. But remember this pin 5, remember that we can kind of inject our own voltage here, okay? So let's do that. Remember, pin 5 is this purple trace here, right? That is our 2/3 voltage, but we can override it. We can reach in with a power supply, and I'm going to connect to pin 5 right here. There we go. I've just connected to pin 5. And now, I can even back out a little bit. That's my power supply there. It's at 4.7 volts. All right. And I can make it go up. And I can make it go down. So yeah, there we go. So if you wanted to use your 555 as a pulse width modulation, there you go, see? Easy peasy. Yeah, it's kind of fun. All right, that's it for this video. We looked at the two comparators, and next time we'll take a look at the flip-flop.